All right, so this is the first class. So we're not starting for 7 minutes till 10 after. And when I have dead time like this, I like to talk about the news because this one of the great reasons we're in computer security is because it's so relevant to daily life. There's news every day. So this is bloody awesome. A few years ago, people figured out that you could make a complete working key from a photograph of a key. So anybody that poses for a modern high-resolution picture with a key in their hand or hanging off their belt, you can copy the key. But this is new. They just need to record the sound the key makes when you stick it in, and they can hear a ping as each pin hits the tooth of the key, and they can deduce the shape of the key from that. So that sounds great, and be fun to see that go. This one I think is extremely interesting and important. It turns out that there have been people that try to estimate how much harm you're doing to a nation by letting people pollute the air. This has been a big thing since the 60s in America, and they've discovered that it is much worse. It kills twice as many people, it makes people sick, it does brain damage, and that means getting rid of air pollution and stopping using fossil fuels would more than pay for itself entirely because of the health consequences of the pollution, totally ignoring the issue about global warming. And this is very important in America, because America, as we know, has a large right wing that totally denies science and says there is no global warming, there is no virus, there's nothing, we don't need to do anything about any of this. And so we could avoid that argument and say, well, forget about global warming. Let's just clean up the air so we can breathe cleaner air. And it would actually save us money. And another big issue is if one nation like the United States cuts down its fossil fuel emissions, but nobody else does, then it doesn't really do any good about global warming, but it does give us cleaner air to breathe. So we would have benefits sooner and and save money right away. So it sounds great. It's very interesting. And this I've seen in my life. I lived through all this in the 60s for Silent Spring, and the environmentalists just had a really negative story about how we're destroying the earth and reproducing too much and killing the animals. And it just was dreary and depressing. And it's hard to get people on board with a movement like that. Whereas a movement that offers you something positive and says you're going to save money is a much better way to sell something. Anyway, here's a big list of bug bounty write-ups, people that have solved computer problems and gotten paid for them. So it's a good place to study vulnerabilities and patches for vulnerabilities, which is what we're going to be doing in this course. I haven't been through any of these, but it's certainly a good place to research. And this is important, especially in the incident response course. We are going through the attack matrix, and we're learning how to do this. These days, when you get hacked by a nation state, you generally are not content just to stop the attack. You also do attribution to figure out who's attacking you, and you'll get it to these names. APT-28, Advanced Resistant Threat Actor 28, is the Russian military, Fancy Bear. It's one of the known Russian military groups, and they attacked using Sandworm here. And this, you can identify the names of the malware used and the names of the people and the groups used and their techniques, tactics, and procedures. And this is commonly what's done. These days, you analyze that and you include it in your threat modeling. GIDRA is a tool we are probably going to use in this class. We're definitely going to use IDA Pro, but GIDRA is the modern disassembler, and it is an NSA product that they contributed to the world, and the book explaining how to use it is coming out next month. So I'm going to get this book and look at it and try to write you some more GIDRA projects. I think we had a couple of GIDRA projects in this course, but I want to have better, more thorough GIDRA products. This is a wonderful tool to use to analyze malware. And we will be playing with it. And I'm hoping I'll find good information in this book. People say it's good. I don't have a copy yet. I don't have an inside track to get a copy before it's out, but it'll only be a few weeks before it's publicly available. And I'll get it then. A student pointed me out to this when I was talking about the cloud machines. They're using in another course. This thing called Eucalyptus lets you build AWS compatible private clouds. So you can connect to Amazon cloud servers and run your own local servers, and they all interoperate together. So that sounds like a pretty great thing to do. These everywhere, if you go in China, and now a lot of places in America, they have these temperature scans before you go in. This is completely stupid and useless. or to be fair, it is security theater. I shouldn't jump to saying it's useless, because the TSA searching your bags and making you take off your shoes before you get on an airplane is also security theater. It does not prevent people from sneaking guns onto planes at all. When they test it, it is ineffective 98% of the time, but it makes people feel better, so they get on the plane. And that's what this does. These things do not prevent you from getting the coronavirus. They do not correctly detect people that are sick. So it doesn't mean that the people that have passed this don't have the disease and that you're safe, but it might reassure people so they feel emotionally better. Anyway, but the point is, these things analyze the temperature of your skin, which depends on the environment. And besides, you can be infectious for quite a period of time after you get the coronavirus before you have any symptoms like a fever. So it's kind of illogical, but it is out there. People, of course, jump on it because it's something they can do, and it's something that people can see you doing, so they feel like you've done something, which is the security theater part. So here's Dr. Fauci, one of the people you can really trust about this, talking about what's going to happen with the pandemic. And what he said here is what I expected, which is 2022. We are clearly going to do absolutely nothing about the virus until January, and only then if Biden wins, because Trump is on the track of just ignoring it completely. And so if they are making a vaccine, however, but even if they succeed in making a vaccine by, say, December of this year, which is the fastest it could possibly be, it's going to take them almost all of next year to manufacture the doses and distribute them. And then half the Americans will not take it. So it won't have much effect to stamp it out. And it probably will only be 50% effective. So anyway, I don't think it'll be years before life goes back to normal. I see a chat. Let me bring up the chat and see what's there. Got to be some correlation of high temperature system. Yes, I think that's a fair statement, Jimmy. So probably there are some people who have a fever and the virus. And so if you scan them with something that only has like a 30% accuracy, and only like a third of the ones with a fever are the infectious ones, then you get like 10% of them removed. So you're right. If you run people through that thing, then there'll be less infected people going past it. So you're right. It has some effect. This reminds me when I was a kid, we would go swimming and there were mosquitoes everywhere and guys would smash the mosquitoes. And I said, oh, there's no point to that. And he said, well, if I smash enough of them, it's got to make a difference someday. And, so in principle, the effect is not zero, but it's not enough to accomplish the goal. Anyway, we're up to 10 minutes after. So let me get to the official stuff for this class, which is here. So hopefully you people know the page. I think I emailed it to everybody. So you go to samsclass.info. And then there is a 126 link here, and that takes you to this class. And we're going to go through some of the stuff in this book, and we're going to analyze the wonderful fake malware in that book. This is one of the reasons I was able to teach this class. This book gives you harmless fake malware to practice on, because if you take a SANS course, you will use real malware, but I can't in a college environment be using real malware because it's not controlled where it goes and it would spread and we'd all get in trouble for spreading a virus. So we're going to use harmless fake malware. It's not completely harmless in the sense that it might mess up the machine you're analyzing it on a little bit, but it doesn't spread and infect other people. So we're going to talk about the types of malware and the major techniques to analyze it. So there is a Canvas system available also, which you get at this City College Canvas. And in there is a discussion board you can put discussions on and you get points for that. There are quizzes you can take, and there are project links you can turn in screenshots and flags you find in your projects. So I've got a schedule here, and I may be readjusting this a bit because some of these projects still use the old Windows 2008 machine, and that's a little too out of date. I'm trying to update everything to 2016. And so if you go down to the projects, there's a group of projects here that use a Windows 2016 machine, and this is what I recommend. There's some here that use the old legacy machine, and I'm trying to update these or replace them. So I'll probably be modifying these projects quite a bit. And then these are fine. These can run either on a cloud or local VM. So we'll talk more about these projects and demonstrate the first few projects a little later. The other thing I should mention is how the grading works. And let me see I'm not sure I got the discussion board. Oh yeah, I have to add the discussion board points to this. But the point is there's quizzes, projects, a final exam, and the discussion board to add up to some points. And 90%'s an A, 80%'s a B, and so on. And there's a lot of opportunities for extra credit so you can make up for things you miss, like quizzes you miss and such. One thing that's new this semester is I'm adding a discussion board to the class, which is to comply with the City College regulation for these online classes. And I decided it made sense. You're supposed to have some kind of meaningful interaction with every student every week. So I've got an assistant to run a discussion board, and there are topics you have to post. And so there should be discussion due dates here, which I don't see. I'm going to have to add them. That's rude. I thought I had them in the schedule, but I will add them. Anyway, nothing will be due until next week, and no dates will be enforced until after the last day to add. So I'll clean this up a bit and add the discussion board due dates to it. But you should go to the discussion board and add a description of yourself first, just an introduction, and then later on we'll be discussing these topics. And you can get extra credit in the discussion board by replying to other people's discussions and by helping people do the projects. If they get stuck, you can ask questions up there about it. All right. So let's start with the first chapter here, which is the basic static techniques and a malware analysis primer. So I've got that here, and I'll start with it full screen, although I'll probably have to shrink it before long. So malware analysis is taking a virus, a computer piece of software that harms a computer, and analyzing it. And I thought this was essentially impossible. The only technique that I knew was to take it apart with a binary disassembler and create assembly language. You would then read thousands of pages of assembly code, which is very difficult. Now, that is one way to do it, but if that was the only way to do it, it would be restricted to a small group of very elite people that can do this very extreme work. And it turns out that there are much easier ways to do it. So here's an example from one of my students that became a tech support person, and they hired him to go to a medical clinic and clean malware off a workstation. And then he called me and said, I feel like this job is not done. And I say, you're right, it's not done. In the modern world, you now have to ask what other machines are infected, what data was stolen while this machine was infected. You know, are the bad guys still in the network stealing more stuff? It's not enough to just clean one machine and feel like a job is done. You actually have to analyze the malware, find indicators of compromise that indicate this machine is infected, and then scan your network to see what other machines are infected. So here's the typical things you have to do after you discover a security incident. I mean, somebody is doing something that's forbidden by your security policy. You have to find out this stuff. Are you currently under remote control of a criminal? Are they really gone? What did they steal? How did they get in? How are we going to stop more people from getting in? LinkedIn is a good example of this. LinkedIn got hacked about 8 years ago, and they tried to just lie about it. They got hacked, and the way we found out was that the hacker could not crack some of the password hashes and posted them on a Russian forum. And people found this list of like 60,000 password hashes, and I looked on there, and I cracked them and found my password on it. So I knew they had stolen my LinkedIn password. And LinkedIn officially said, no, we haven't been hacked. That thing is just fake. We hadn't been hacked. And various other people like me said, dude, you've been hacked. That's my password. You're lying. And LinkedIn tried to lie for about a week. Then they couldn't lie. Then they issued a statement saying, all right, we got hacked, but we asked our lawyer, and the lawyer said, we don't have to do anything, so we're going to do nothing. We're just going to totally ignore it. And I said, I don't really think that's going to fly. And eventually they did have to clean it up. But this is the modern evolution towards incident response. Nowadays, people understand when you get hacked, you really do have to do something about it. You have to find out what happened. You have to clean up your network. You have to explain to people what happened to them, offer them things like credit protection and stuff like that. So this means part of the job of incident response is analyzing malware. You find that somebody has infected your machines and they're controlling it. So you have to decide how this malware works. You have to find out how to identify it, how to clean it off, and so you can find where it is and get rid of it. So here's what malware analysts do. They have to figure out what happened and how to find the other infected machines, how to contain the damage, and then how to prevent it in the future. And that might mean signatures for your intrusion detection system to notice if they try to do it again. So yeah, the most common way to use signatures in an intrusion detection system or a antivirus system on a machine is with signatures. These are unique pieces of code, hopefully, and the point of this is you don't have false positives. If you see a code then you know you were infected. I see a comment very different in the public relations of TJ Maxx. Yeah, TJ Maxx made a big scandal, and so the public relations made him do it because, yeah, that's right. See, the reason why I think LinkedIn could ignore it is because it was not credit cards. The common people understand that when they use a credit card at a store and that gets stolen, that's bad. Whereas all LinkedIn had was like your resume, which you had posted publicly to get a job. So their lawyer kind of had a point saying this information is not that private, although the password kind of is. But at that time, passwords were not considered PII legally. But anyway, it's a good point. Anyway, then you can have network signatures, which are the same. Some kind of signature of a series of bytes you'll see in network traffic, which would mean you recognize that you have had a malicious file go over your network. The problem is you don't want to have false positives. And we had this happen at City College. In 2012, we had a chief technology officer at the college who was a crook. And he had, at several previous colleges, done the same thing. He would hire his friend, who was a network forensic analyst, who would then analyze your system and tell you you're all infected, and then charge you a bunch of money to fix it. And so he didn't tell anybody at the college, but went straight to the press to create a scandal so he could then make a big show of cleaning off the network and claiming to be a hero. It was a scam, and it was pretty effective, and it made a big deal, and it was all completely wrong, but his friend doing the network analysis might have been actually doing somewhat more or less reasonable, because what he did was he found what he said were 200 Windows viruses on our Linux DNS servers. And I think what he was doing was taking a list of known command and control server IP addresses. And when a machine connected to that IP address, he interpreted that as it being infected. But if you have an email server, every time it receives an email, it then does a reverse DNS lookup back to the server it came from to find out if that server should be sending email, to see if that email is spam. So there are requests that go back to malicious servers that do not mean you're infected by malware. They just mean you got some traffic from that server and you sent some kind of request back. You'd have to look more deeply into the request to tell if it's really malware beaconing back, indicating that you're owned and under hostile control, or if it's something like an anti-spam solution, which is what I suspect it was. Anyway, so in the modern world, there are 4 basic malware analysis techniques, and we're going to do them all. The simplest, there's 2 ways they split. There's static and dynamic, and then there's basic and advanced versions. Now, static analysis is where you examine the malware without running it. And so the advanced static analysis is when you use a disassembler like IDA Pro, and that's the only technique I knew 10 years ago. That's what is so difficult. I said, boy, this is not worth learning or teaching. This is just miserable with thousands of lines of code. But you can also use tools like VirusTotal, Strings, and what these do is they let you analyze malware without looking at the code. VirusTotal will just compare it to all the antivirus engines and see if somebody else has already figured out what it is. That would be sweet. And Strings is very nice. It just lets you see all the readable text in the code, and you can often guess what it does just by looking at the messages. So you don't, again, have to read the code. So you use these easy techniques to go as far as you can, and you don't bother with the difficult technique unless you have to. Then dynamic analysis is really fun and effective. You have a virtual machine that you can afford to throw away, and you run the malware in it, and then you run monitoring tools on the infected machine while it's getting infected. Now, when I first heard this, I said, that's terrible, because how can you trust the tools that are running on the compromised operating system? And here's where you get the fundamental secret here. None of these techniques are perfect, and you just accept that. This is the same thing with cops in the cop shows, trying to find blood spatters and gunpowder traces and figure out who committed a crime. None of the evidence is perfect. None of the witnesses are perfect. None of the video footage is perfect. And yet you accumulate evidence until you have enough confidence that you've solved it. So you use this technique, even though it is possible for malware to hide from these techniques, but usually it works. And so you try using the easiest techniques and see if you can find what you want, and then you use the hard technique if you have to. So we talk about malware as VM detection. Yes, in general terms, I don't think we'll have any live examples of VM detection here. However, if you want to see that, if you get a chance, take an Android malware course. I've taken a workshop there. If you have an Android malware, you can't run it in Android emulators at all. It all detects emulators. You have to have real hardware devices. There's not that much malware that detects virtual machines yet, as far as I know, but it is there. It's a good point. Anyway, so here's some tools. Redshot lets you compare a registry at one time to a registry at another time, so you can see what registry keys were changed. Process Monitor and Process Explorer are internal Windows tools that are wonderful. They'll let you see what processes have been launched and what actions something has done. And Wireshark lets you analyze network traffic, and volatility you can use to analyze memory. So these are all useful tools to analyze the infected machine and see what the malware did to it. So basic static analysis is where you don't even look at the instructions. This is like feeling a Christmas present without opening the box. You just squeeze it and rattle it and try to figure out what's in there. It's not very in-depth, but it can work. Basic dynamic analysis is where you just run it and see what it does. And you make some sleazy assumptions, like you assume that the malware won't notice that it's in a virtual machine or turn off your tools or anything. And so if it is not very smart malware, they'll get the truth. And if it is smart malware, you might get lied to. But that's something you have to get used to. All your tools have a fairly high probability of failing and lying to you, and you just have to accept that and remember not to trust them too far. Advanced static analysis is where you take a disassembler and you take apart the code, and now you read the code. In principle, all the information you could ever want is in there, but in practice, it takes too long to read, so this takes skill. It's best to focus on just a small part of code that you decide it's important with the other techniques. And advanced dynamic analysis will do, which gets easier again. This is the most difficult technique. Advanced dynamic analysis gets easy again. You run the code in a debugger, and the debugger lets you see what the process is doing. It lets you stop the code and modify it. And so it's very nice, and we'll do quite a bit of this using Windows malware in a debugger. By the way, this course is only going to do Windows malware. We're not going to do Linux or Mac malware. Windows is the main area where it matters, and that's what we're going to study here. So here's common types of malware. A backdoor gives the attacker some extra administrator account or some other way to control a system. A botnet means a machine is under control of a command and control server that can issue commands to it. Downloaders run just to download further malware, so they're part of staged malware where you'd have an infection, and that infection infects you with another product and another, which is typically how it's done, because the initial hook that you use to get into a system often lets you run only a small or limited series of commands. So you run a small piece of code which downloads a bigger tool. Sniffers, keyloggers, and hash grabbers steal information from the system. Launchers launch other programs. This is often done to avoid antivirus. We'll play with that a bit. And rootkits hide malware so that it cannot be seen by other software on the machine. They compromise the operating system at its core so that other tools that do something like run a directory will not even see the files that are hidden by the rootkit, because it has altered the kernel call that performs the directory function. So rootkits are the most dangerous kind of malware, most difficult to detect and remove. And then there's scareware, of course, that frightens you into doing something, putting up boxes saying you've been detected, going to porn sites or something and try to trick you into paying somebody. And one common type is ransomware, of course, that encrypts your files and then puts up a box saying you have to pay to get them back. Malware that sends spam, viruses, and worms that spread. Now it's almost all worms. Viruses are from back in the days of floppy disks, but people use viruses as the slang term for all malware these days because it's so colorful and people have an idea what it means. So mass malware is where you send many copies of exactly the same file to many machines, and this is what antivirus can stop. They eventually get a copy of it, they put a signature in their antivirus definition, and now it'll stop it everywhere. So this is a sleazy technique that's not terribly effective against a strong defender. Targeted malware is when you're seriously directly attacking one company, like Stuxnet. The Americans and Israel decided to shut down the nuclear isotope centrifuges in Iran, and we carefully designed malware that would just affect those devices, and it would spread through Windows machines through the whole world, but not harm them. And so it found the correct target and then attacked that one machine. And that means somebody put a lot of work into targeting you, and that's what the advanced persistent threat actors do. This is what typical spam operations and such do. They just throw out junk that has a low probability of infecting somebody, and they just hope to get a few people that will have an old unpatched system and run it and get infected. This is just a cheap common attack, and that's what common defenses like antivirus can stop. targeted attacks are very difficult to stop. All right, so here's some general rules for malware analysis. The main thing is you don't want to learn everything about the malware. You could write a whole PhD thesis analyzing malware, and most of us are not interested in putting that much work into it. You just want to find a few simple things. I want to find out what harm it did, how to clean it off, and how to detect it on other machines. Now, I do not need to understand 100% of its functionality to do that. I just need to find a couple of indicators of compromise, like a file or registry key it creates, and I want to find some way to clean it off, and I want to find some way to detect what harm it did. So you have a lot of tools. If one tool fails, try another. The malware will often break your tools because the bad guys have the same tools and they're designing their malware to evade or alter these tools. And it's, of course, constantly changing. So once you learn a technique, it will only work for a little while until the bad guys realize, well, people can stop that one. I have to up the game and make nastier malware that's harder to stop. So let's try some Cahoots. I've got them here. This is 1A. And that's good. All right, here we go. Okay. Looks like this is too loud. All right. So go to kahoot.it and put in that pin. And this is worth extra credit if you get the most right. The top 3 get extra credit. You're not required to do this, but it kind of breaks up the lecture. Most people like it. On every class, there's always a few people that prefer not to do it, and you're by no means required to do it. Yeah, not Petya. Yeah. Good. Got 36 people in there. Okay, so I'll wait a while. We might have quite a few more. All right, I'll give it another 10 seconds, unless we get more people. Okay, they're still coming, so I'll wait a bit yet. All right, another 10 seconds now. All right, looks like that's it. All right, which one involves you deliberately infecting a computer? That's dynamic analysis. The malware is running. All right, let me move this out of the way. All right. So, which one can find many infected computers from a single Horta measurement? Network signatures, if your malware will send out some characteristic network traffic, then you can find out who's infected by looking for that network traffic. All right, what technique involves running parts of the code and stopping? Okay, that's a debugger. All right. And which one may alert attackers that you've detected the intrusion? Yeah, I think I did not mention it as it went by in the slides, but that's a property of VirusTotal. You can send malware to VirusTotal for analysis, but they will send it to antivirus companies. So if it is targeted attacks unique to your company, that will alert the bad guys that you're on to them. So if you want to use VirusTotal in an environment where you're afraid you're being attacked by advanced resistant threat attackers, what you do is you hash the malware and you search for the hash in the database, because that will let you see if they know it. And if they don't know it, they will not get a copy to forward. Anyway, that's a useful fact. It violates your operational security to use VirusTotal in a high security environment. What kind of malware spreads? Okay, that's worms. All right, good. All right, and what malware conceals other code? All right, that's rootkits. They can hide the presence of other files and processes. All right, so winners. NotPetya will have to tell me who they are if they want their points. Elam is a real name, I know that. And Gene is probably a real name, but there might be another Gene. So if you want to make sure to get your points, put your real name in the chat. Ah, here we are. Okay, good. NotPetya, I see who you are. All right, anyway, let's see, not that I know from experience, but VirusTotal will remove samples if you accidentally upload them. Well, yeah, but that doesn't mean they didn't tell the antivirus company. That's right. Another thing about, yeah, that's right. But, you know, in principle, it's considered best not to use them in a high security environment, or to use them as I described, just on a hash. But yeah, anyway, so basic static analysis is where you run your antivirus to scan on the malware, you look at hashes and compare it to a list of known hashes, or you look at strings, the readable text in a file, or the functions it calls, or the header parts of the file. So antivirus scanning just looks through the malware for some kind of recognized signal. VirusTotal is one easy way to do it. It'll run it through 50 or 60 scanners. It's a Google service now. Hashing is a way to uniquely identify a file. You can do MD5 or SHA-1, or you could even use one of the newer SHA-2 or SHA-3 hashes. And these will uniquely identify a file like a thumbprint. So now you can search for that hash. And if other people have found the same file, there might be a record of it up there. Windows doesn't come with hashing utilities built in, so you have to download a tool like HashCalc or some other tool to calculate hashes. So you can also use it to label a file. You can share it when you publish information about the malware after you analyze it. And other people are doing the same thing. So searching for a hash is often how you do it. When people publish lists of indications of compromise, they often include hashes of files. One good thing about it is even if a file has a different name, the hash will be the same. All right. And strings, look for any series of printable characters. Now, in the Linux world, you often use plain ASCII strings, where it just looks for a series of bytes that are printable up to a certain length, like 6 characters or more, and prints them out. But in the Windows world, it's almost always Unicode, and it's this particular old-fashioned 16-bit Unicode. So it's 16 bits per character, so you have to use a tool that can detect Unicode, and McAfee makes one called bintext that we're going to use. So here's a character in ASCII. You have 3 letters, BAD, and a null terminator. but on Microsoft systems, it would be here in Unicode with a null byte after each character. The 16 bits are here in case you use something else like a Chinese character. But if you're writing English, then every other byte is null. And you have to have a string detector that can read that kind of string. So we talked about this, that's strings command in Linux, and you can prove it into Windows also. So if you do find strings on a file, you'll find some short things that are just random characters. This looks like an IP address. This looks like a Windows library, and these look like Windows function calls. And you get used to seeing these things, and a lot of malware analysis is just understanding how Windows software works. That's really what we're going to do. So if you take a Windows development course and learn how to write, say, Visual Basic code in Windows, you'd learn a lot of the same information. We're just looking at it from the malicious side instead of the good side, but it is the same information. So bintext is the tool we're going to use. This is a nice GUI tool, and it finds ASCII or Unicode strings. So here it's run on a sample. This is Notepad. So here you see the libraries Notepad uses. It uses kernel 32 and user 32 for user interaction and advanced API calls. And it uses ntdil and other functions here. So those are just a series of libraries used by this code. Another thing that you'd often do is pack malware. If you have a file, you might zip it just to make it smaller, but you also might pack it to scramble the strings. So the strings tool won't work, and so perhaps antivirus won't be able to recognize it. You take your original executable and you pack it, and then you have a little unpacker at the top, like a self-extracting zip file. So this is a common technique to make malware smaller and to make it harder to analyze. So if you use PEID, it's a useful tool. We're going to use it a lot. This gives you a little bit of information about how a file is built, looking in the headers, and it can detect certain packers. This detects the UPX packer, which is a common open source packer. It'll also detect if it's unpacked what language it was written in and such. This is reading the header to find out the surface information, which tells you how this file is made. So we'll use UPX a little later, and you'll see how it works. But here I have a file that was packed, and when you unpack it, it gets bigger. So the packed file is 272,000, but when you unpack it, it's 592,000. It gets bigger. And when you look at the strings, the packed version has 23,000 strings, but the unpacked version has 33,000 strings. So it's a game here. By the way, be aware that all your malware analysis tools might run the malware. PEID will sometimes do that. So you can't use your system that's important to you, that has your real login details or anything in it, to do any malware analysis. You need to use a virtual machine or a cloud machine that's used for malware and not also used for web surfing and emailing and shopping and other purposes like that. Because as soon as you're putting malware on a system and playing with it, you're taking a chance of getting infected and having that malware do bad things. So you should not do it on a machine that you value. All Windows executables are portable executable files. This is the generic term for it. EXEs and DILs and other COM files. And this is a file format that has a header, which specifies what libraries to load and other information about the file. And then it has sections. So LordPE is one of the many tools that can analyze malware. And it will show you, analyze Windows executables really, and it will show you information about it, the size of the header, and here it shows you the sections. So this file, which is Notepad, this Microsoft text editor, has got a text section, a data section, a resource section, and a relocation section. You can have as many sections as you want, but every program has to have a text section. That is the actual executable code, and they almost always have a data section and a resource section also. Data is strings and other information it uses to print out messages. And the resource section typically contains graphics and icons and things like that. So almost every Windows file has those. And it might have the relocation section, which is used to reposition it in memory if the memory it wants to live in is already occupied by another program. You can have a lot more sections, but those are the main ones you'll see. All right. So I've got a few cahoots about that, which should be here, 1B. All right. All right, I'll give it another 10 seconds. I think 24 is how many we had last time. All right, so all right, what's the mathematical value that uniquely identifies a file? Okay, that's a hash value. Good. Ah, somebody got it perfect. Got it as quickly as possible. So what technique finds the readable text in a file? Okay, that's strings. Extremely powerful. So easy, and you can often tell what you need to find out just with strings. It's usually the first thing I do. All right. All right, what file type has the header specifying things like text and data? That's PE. Windows executables are all PE files. All right. So what kind of file is shared by many different programs? The DIL files, dynamic linked libraries. All right. NotPetya is up to 6 points now. And Mateo, good. And Stephen, all right. Good. All right. Well, I think we can go to the next section here, which is here. Okay. So we'll talk more about these libraries. You've got, if your program uses a library, then it imports functions from the library. So code, you can run a function that you did not write, Microsoft wrote it, and you import Microsoft's library typically. So you do this by linking. There's static linking, runtime linking, and dynamic linking. Static linking is used in Linux, but very rarely in Windows. This is where you take all the library code you need and put a copy of it in the executable. So if you use networking, you copy the whole network library or the parts you're using into your code, and that makes your code larger. And if some other program on the computer is also networking, it has a second copy of the library code. This therefore wastes memory, it makes files bigger, and it makes them load slower, but it means they run independently. So it's not common in Windows. What's runtime is where you change the library during run. You decide to do something, you connect to a library only when it's needed. And there are functions, API calls in Microsoft to do this, like load library and get process address. This is something normal code doesn't use that much, but malware uses it all the time. So malware does a lot of things that are suspicious in the ways it handles libraries, but the most common method is dynamic linking. This is where you run the program and it knows it needs something, and it looks to see if that library is already loaded in memory because some other program is using it. And if it is, then your code uses the library that was already in memory. Therefore, it doesn't bother loading any extra copies of it, so it uses less memory, and your program loads faster, but it's kind of unsanitary. You're sharing code with another program. But that's what Windows software does almost all the time. So the PE header lists every library and function. Your program could not launch properly without that information. And you can find it in the strings, and you can find it in a variety of programs that let you view the header. So if you see the URL download to file, that's a Windows library function that does just what you think it does. It downloads a file from the internet, so that indicates that this program is downloading files. All right, so Dependency Walker is one of the tools to fix this. This shows you all the dynamically linked functions, and the purpose of it, as you might guess from the name, is to help resolve missing dependencies. You've probably seen it when you launch a Windows machine program and it says missing DIL file. I need x472.dil. That's when it needs a library, but it can't find a library. And so Dependency Walker is to help developers prevent this problem. So when you launch something, it will then list all the DILs that it needs and check and see if it can find them and tell you if it can't find them and help you resolve why your program is trying to load libraries and can't find them. So here's, for example, is the real Windows services.exe that is used to run a whole lot of background services. And as you can see, it uses a lot of libraries. Here's a malicious piece of malware with a name that looks like services, but it isn't. And one thing that's very suspicious about it is it uses almost no libraries. Almost no legitimate program could possibly do anything worthwhile with so few imports. So that's a clue that it's malicious. That's a suspicious behavior. So in Dependency Walker, you have the imports and you have the exports. If you are an executable file, you will typically, everything has imports, which are the functions it uses. Exports are services it would offer elsewhere, and you usually don't have very many of them except an entry point in executable files. So here's some common DILs, and you need to know a few common Windows libraries. Kernel32.dil is very common. This is the normal library used to execute kernel functions, and in the Windows environment, you cannot directly use the hardware at all from user space where programs run. If you want to print something or connect to the network card or read the keyboard, you're not authorized to do that. You have to ask the kernel to please do that for you by using a Windows API call, and you typically do it through kernel32.dil. Here's advanced features like the registry. User32 is in almost every program. If you want to pop up a window and have buttons to click and things like that, you need User32. And GDI has got graphics functions. NTDIL is the direct interface to the Windows kernel. This is the Windows NT. This is the kernel itself. NTOS kernel.exe is the kernel, and ntdil.dil is the library that goes to it. And this is the native API, which is not supposed to be used by userland code. So malware often uses it, but legitimate code generally does not use it. Instead, it uses kernel32.dil. And then there's networking DILs here, WSOC and WS232. These are low-level Berkeley standard sockets, which are a difficult way to use the network where you have to handle the handshaking and everything yourself. So this is something a lot of malware uses, but normal programmers would avoid using these difficult functions. They would use wininet.dil that has high-level functions like download a file from a website all with one call, instead of having to handle the whole handshake and packets one by one, which is what you'd have to do here. So DIL's export functions and EXE's import functions typically, and they're both listed in the header. DIL's export functions, because it's a library, it might have 50 functions, and it will offer 50 points to enter. If you want this function, enter here. If you want that function, enter there. And EXE typically imports functions, but it doesn't have very many exports. It typically just exports a main, which is where you start, and you're not supposed to run the EXE from any other address except the starting point. So here's notepad.exe. Here's its import table. It loads registry query value, is text Unicode, allocate something, unlock, unmap view of file. You know, it has a whole long list of calls that are used. Here's advapi.dil. It has an export address table, so it exports all these functions. Add ACE, access control entry, access check by type, abort system shutdown, and that's just the A's. Hundreds of functions in this library. And it exports all those labels which can be used to hook into it from programs that call it to use those. Here's iTunes setup.exe. Here's the way a raw program works. So in PE view, we're using here, you'll see the structure of a PE file. Here is the raw hexadecimal display of the file. Every file, every Windows executable starts with MZ. You can recognize that as a fingerprint. Those are the first 2 bytes. Then they always have this program cannot be run in DOS mode. And then down here, after the header information here, they will have the NT headers and then section headers for each section: text, our data, data, resource, relocation. Then they'll have the sections, then they'll have the import table, and so on. And they may have a certificate if it's signed code. I'm not sure if that's the right digital signature to sign this code, but it probably is for iTunes setup. Anyway, so if you have a keylogger, it can import user and use set Windows hook, which is a common way for keyloggers to work so that they capture key presses and run them through special code. It might export these functions to send the data somewhere so your malware can be used by something else, and it can use a register hotkey to assign a special key press to be used to take the data off. Those are possible things it might do. If your program is packed and you have not unpacked it, then the only thing you're going to see is the unpacker, and it probably does very little. It's kernel 32 and user 32. It pops up a message box and just has a few functions to unpack it. All right, so here's common sections. The text is the one that contains the assembly language instruction, machine code if you want to be technical. You have to have a text section or your program is not going to do anything. And they typically need our data and data for imports and exports and global data, and resource for things like icons and some strings. All right. And here's PE view that we've already talked about. If you go to the image file header, it will tell you things like when this program was compiled. And that can be useful. Sometimes that's used as a clue of what nation made the malware. It's a time date stamp. But of course, it's not verified in any way, so it could be fake. Here you see the size of the file on disk, and some packed executables have a virtual size much larger than the size of the raw data, which means the actual size when it's running will be bigger than the packed size in the packed file that's running there. So here you got a virtual size of A68C, but the raw size is A800, so this is not packed. Those are pretty much the same. If it was packed, they might be quite different. That's Notepad, so it's not packed. Here's another one for a packed program. You'd have large virtual size, but the raw data has got a size of 0 filled in. Anyway, Resource Hacker is another tool that lets you wander through the resource section. It's used by sort of gamers to change the look of games and such. Lets you see what's in there. You'll see in here a list of icons. Here's little graphics, little calculator symbols and such that are here, so you can see what images are used by the software. All right, here's 1C. Let's look at this, and then we'll take a break before I go through some of the projects. So we're here. All right. All right, give it a few more seconds. All right. Okay, which one makes an executable large? Static linking makes an extra copy of library code so the executable gets large. All right, what's the most common way for executables to run on Windows? Dynamic linking with DIL files is the normal way you do it on Windows. All right, which library lets you use FTP? CNIT is the high-level library that lets you do FTP with a single command. These functions don't use networking at all, and this is low-level Berkeley sockets, which make it very difficult to do a high-level function like FTP. You control network transactions one at a time. CNIT is the normal thing you use to do network communication. Which library puts up pop-up boxes with buttons? User 32 to interact with the user. By the way, these 32s all over the place mean we're talking about 32-bit code, which is the most common kind of malware. But some of it, of course, is now 64-bit code because a lot of people have 64-bit machines, and then you use 64 instead of a 32 in these names. All right. And what library is not normally used by EXEs and might indicate malicious intent? Yeah, that's NTDIL. The direct kernel library is not normally used by ordinary developers. So I had Leighton and K. I think I know who that might be. And Stephen again. Stephen's a 6. All right. So let me stop this recording. I'm going to leave the share going.